gets developed uh, inside any member because of just being the material properties. Both of them uh, are actually material properties, whether that be stress or that be strain. And we discussed about number of things. We discussed about factor of safety, and we discussed about elastic region and plastic region with regard to the stress strain curve of steel. Now let's do some problems in order to get more hands-on on these things, that is stress and strain. Let's say we have first problem. It's a simple problem wherein we have a simple elastic rod. Okay. Uh, we have an elastic rod of 25 diameter, 200 long, and it basically okay, let me write it. Elastic rod 25 in dia, 200 long. It extends by 0.25 mm under tensile load of 40 kilonewton. We have to find out intensity of stress, find the intensity of stress, we have to find out strain, and E, that is modulus of elasticity for the material, of rod. Okay, now that we got to know that it is a circular rod because diameter is given. So first of all, before going, we should be able to understand what is given in our problem. We have 25 rod. Let's say this is a rod. It has a dia of 25 and its length is 200 long. And we have actually this rod has been extended under tensile load of 40 kilonewton. Okay, under tensile load of 40 kilonewton. So tensile load means that the rod is being stretched out. That is what we understand by tensile loads, which is how much? 40 kilonewton, 40 kilonewton. Fine. So before we can get hands on calculating the intensity of stress, we already know how to calculate your stress. What is the formula to calculate stress? It is simply load per unit cross-sectional area. Right? We already know how much is your load. Load is your 40 kilonewton. Let's bring it in newtons. That means 40 into 1000 newtons. And we know our area for this circular rod is, it will be pi by 4 d square. Okay, and you can calculate that pi by 4 d is how much? 25 square. That will be equal to, please do the calculations quickly. It will be somewhat 491 square. Okay, now you have to calculate your stress. It will be simple. Load, that is 40 into 10 raised to the power of 3 divided by 491. For with regard to units, you will be having now Newton per square. Because for load you have Newton, right? And for area here you have mm square, Newton per mm. Therefore, the values will be 81.5 Newton per mm square. This is your intensity of stress. Simple. And then you can similarly calculate your strain. What is the formula for calculating strain? It is actually change in length divided by its original length. If you will go back to the given data in your problem, it says that the rod is 25 dia, 200 long, and it extends by how much? 0.25 under tensile load. That means change in length is how much? Change in length is actually 0.25. And how much is the total length? It is 200. Okay, that comes up 0.00125. This is your strain. And it is unitless now because 0.25 200 they'll cancel out. Or you can even say strain is 0.00125 per mm. Okay, if you want to get a closer look of it. Now this was with regard to what? Calculating stress and strain. Then if you want to if you want to know what will be the modulus of elasticity on the basis of stress and strain of this very material. I have not, nobody has talked whether this is a steel, this is aluminum, this is wood, what is this? Nobody knows about it. We have simply mentioned an elastic rod. Right. If it would have been steel, then we know the modulus of elasticity. Steel is how much? Modulus of elasticity of steel is 200 GPa. But as of now, we are not in a need of that. We will see what will be the modulus of elasticity. So, in order to calculate your modulus of elasticity, you know it is equal to stress by epsilon strain. Okay, then giving the values of stress, how much is your stress? It is 81.5 divided by 0.00125, and your value for modulus of elasticity comes out to be 0.625 into 10 raised to the power of 5 Newton per square. Okay, this is your modulus of elasticity for this particular type of material. Okay, now this was regarding one of the problem. We'll be doing one more. Sahil, am I audible? I hope network is better today.
Yes, sir, it's good.
Okay. Now let's say we have one more type of problem, which is like okay. We have two cylindrical rods actually. We have two rods. This is rod 1, and then we have one more rod attached to it, and it is fixed at end A. Okay, they are basically welded, or yes, we can say the two rods of different dia now here again. They are circular rods. They are solid cylindrical rods actually. It's welded at a point. Let's say this is B. They both are welded together. Now, what we want to know is that for a load of 45 kilonewton, here I have applied a load of how much? 45 kilonewton. Okay, I want to know what will be the dia D1, and here we have D2. Now I need or I have two cylindrical rods having a dimension of, let's say it is 200 625 mm, and the another one is 750 mm. Okay, I have two rods and their length is 625 mm, and the another has 750 mm. And the load that is going to come at the bottom, let's say point C, is 45 kilonewton. Okay, and allowable stress for the material is 150 newton per mm square. Okay, 150 newton per mm square. What I need now is, now that I know the allowable stress is 150, I know the length of both the cylindrical rods, and I know the total load that will come upon at point C. I want to know what should be the diameter D1 in order to cater this amount of load within allowable stress. I want to know what should be D1 and I want to know what should be D2. On basis of what? On basis of allowable stresses. This solid cylinder must be having some limit to undertake stresses. We cannot say that this material will take any type of any sort of stress. It can only take up to, permissible limit is only it can take 150 newton mm square. That is it. If the stress is more than that, the member can fail. Member can fail. So firstly, what I
इस
need to
क्वेश्चन के
know
लिए
is,
पर्टिकुलरली गिवन है, मतलब क्वेश्चन में ही गिवन है अलाउेबल स्ट्रेस इज 150.
yes, we have two loads actually here. At point C, we have 45 kilonewton, and at point B, again here, we have 60 kilonewton.
In those
Yes,
same.
a bit louder, Jalka.
So is the material for both the rods same?
Yes, it is same for both the rods. There are actually various cases, we will go through them, wherein you will have composite materials. Composite materials means you will be having two type of material welded together. So in that case, your given criterias will be different. We will look into those problems also. Now, with regard to this problem, we have two loads. One is at point B, that is 60 kilonewton, and another is at point C, which is 45 kilonewton. Okay, and the allowable stress is already given. The length of these solid cylinder bars is already given. That is 625 mm, and another is 750 mm. Okay, now with regard to this type of loading, you can easily say the load is in tension, or the stresses induced in the material will be tensile stresses, because if it is going downwards and at the fixed end it will be in the opposite direction because it has to resist it, right? So in order to resist it and bring it into equilibrium, it has to give the tensile forces or tensile stresses. So firstly we will see what is the total tensile forces. Tensile forces, that is, as you already have mentioned, it is 60 plus 45, that will be 105 kilonewton. Fine, this is the total tensile forces on both the bars, or this tensile forces will be resisted by point A, that is the fixed point A. Fine. Now, how much is the area, or let's say the allowable stresses? Allowable stresses as we already know, the stresses that actually come on the bars with regard to what? With regard to the load that is actually there. I can simply say that stresses will be simply equal to 105. Therefore, you can write 150 is the stresses, and then we have load. How much is load? 105 kilonewton, and we have area, cross sectional area, right? In order to calculate the dimensions. This is stress, or sigma is equal to load per unit area. Let's say this is your P, and area is what we are in need of. This is cylindrical. And now area will be equal to 105 into 10 raised to the power of 3 Newton divided by pi by 4 d1 square. Let's talk about rod AB first. This is for rod AB. This is for rod AB. So you can calculate your D1 square, or D1 will be simply do the calculations quickly and tell me how much is your D1. Quickly. Give me the value of D1.
29.86.
How much?
29.86.
Okay, it is 29.86. So you have calculated the amount of D, or diameter, for what? For the amount of load, which is how much? 105. And keeping in consideration the allowable stresses also, which is how much? 150. Both the criteria are fulfilled. And you got to calculate the D1, the minimum amount of D1 that should be in order to resist this load. Okay, now when you talk about uh, another member which is quite thinner than this, you need to calculate what? You again need to calculate your D1, sorry, D2. You are in need of calculating D2 now. Now, firstly, you will say, what will be the total tension in the rod? How much is, how much are the tensile forces or tension, or tension in BC? It will be now only 45. Right? It will be 45 kilonewton, because on the bar BC you have only 45. But when you calculated what? Tension on bar AB, there we had two types of forces. One was 45 and another was 60. But for BC, you only have 45 kilonewton. Fine. So again, and tensile and allowable stresses are how much? 50. So you can again give the values. 50 Newton per mm square is equal to 45 kilonewton. So we will bring it to Newton only. 45 into 10 raised to the power of 3 divided by pi by 4. How much is your D now? That is what we need to calculate. That is D2, D2 square. So give the values and calculate D2. Tell me how much should be D2.
19.54.
19.54. 19.54. What should be the units? mm, right? We are talking in terms of mm. Newton and mm, and Newton per meter square is is Pascal. So you must be knowing that. So this was with regard to this problem. Let's say we have one more problem now. Okay, we have another hollow circular column. Okay, we have hollow circular column. Let's say this is our hollow circular column, and it has a height of 3.5 meter. Fine. And external dia of 350. External dia 350 mm. And now it has to support an actual load of 6,000 kilonewton. It has to support an actual load of how much is your actual load? 6,000 kilonewton. Fine. And it is already given in the problem itself that the stresses in the column should not exceed 150 Newton per mm square. Again, it is given that this column should not exceed 150 Newton mm square. That means, again, your allowable stresses are how much? Allowable stresses are 150 Newton per mm square. Okay, and it has been seen on application of these loads, there is decrease in length of the column. Okay, and the decrease in length of the column should also not exceed 2.5 mm. Decrease in length should not be greater than 2.5 mm. That means up till 2.5, the structure will be safe, and beyond that, the structure can fail. It can only take this amount of change in length, that means decrease in length. Now we have to find out maximum allowable internal diameter. We have to find out allowable internal dia. Let's name that as D. This internal one, because there will be some thickness, right, of this cylindrical column. Now I want to know how much amount of thickness is needed for this very hollow circular column in order to take how much amount of load? 600 kilonewton. And I also know that allowable stress, that it should not exceed, the material should not exceed 150 Newton per mm square. And I have one more condition, that the decrease in length should not be greater than 2.5 mm. Okay. Now let's say here I'm describing this material to be steel. So modulus of steel, we already know that is how much? 2, or we can write it 2 into 10 raised to the 5 Newton per mm square. 2 into 10 raised to the power of 5 pascals is modulus of elasticity of steel head. Now we have two conditions which need to be satisfied. Firstly, we have allowable stress, and then we have a slab of maximum strain, maximum allowable decrease in length, which is also 2.5. Okay. Now, first of all, we have condition or calculating our strain, right? Strain is already given. We have a condition which says that stress is actually equal to modulus of elasticity times epsilon, that is strain. And given the values, we can simply say stress is how much? It is load per unit area, that is equal to modulus of elasticity times change in length and actual length. So in order to calculate now change in length, that will be equal to how much? PL by AE. Okay, PL by fine. Or we also know that what is P by A? P by A is now our allowable stress, which is already given. And there is one more thing which is given, that is change in length. It is also, these two things are being limited, right? And the value is already given. So we can write this equation simply as change in length will be equal to P by A is your stress multiply length, total length divided by modulus of elasticity. Okay, and then we have the value of change in length. How much is that? 2.5 mm is change in length is equal to allowable stresses. How much are they? 150 multiplied by the length. How much is your length? Or what we can do here is we can even check before applying the values of your stress, this stress. We will not apply the values of allowable stress first. We will see, before we can go further, we will see on the basis of criteria that the decrease in length should not be greater than 2.5, and as per the length of the beam, we will first try to understand what will be the stresses, what will be the stresses induced, and those stresses will be actually how much? It will be E times delta L divided by L. Okay, and those stresses are, E is your 2 into 10 raised to the power of 5. How much is the cap on a decrease in length? It is 2.5. And then we have the actual length. How much is that? 3.5 meter. That means it will be 3.5
So 2 multiplied by
meter
10, 10 to the power 5 or 10 to the power 3?
5. It is 5. It is 200 GPa, na? So correct
आपने
it
पहले
if
3
you have
लिखा था
written.
ना?
No, it is 5. It is 5.
Okay.
Okay, and then we have the length, 10 raised to the power of 3 again. And we will get stresses, and that will be equal to, please calculate it, how much will be the stresses? Quickly tell me how much are the stresses?
142.85.
Sorry.
142.85.
Okay, good. So here we have calculated the stresses. How much amount of stresses are actually coming on this very hollow cylindrical column. So it is, stresses are how much? 142.86. Okay, 142.86 Newton per mm square. And how much are allowable? Sigma allowable are 150 Newton per mm square. Now, the stresses that are coming on this circular column are only 142. and allowable are 150. That means we are on the safer side. Okay, if it would have been more than what was allowable, if it would have been 150, 155, then in that case we had to redesign the length, and we had to redesign the amount of load that was actually coming on it. Because if that would have been the case, then this hollow cylinder could have failed. Okay, now that the allowable that was given was 150, and the actual stresses, this first one is actual, and the actual stresses that are actually coming is only 142. Therefore, we can say we are in the safer zone. Okay,
So apart from the
now
concept itself, in this question, isn't it a futile exercise to do this?
why?
Matlab, in these kind of questions, isn't this a futile exercise? Matlab, do we
That
have to
I'm
check the
asking
given
you why.
parameters?
Huh?
Do we have to check the given parameters if it is already given? Isn't it a
No,
futile exercise?
listen. You need to understand here now. Now, while you have to design it, design means that you want to know what should be the internal dia system.
Right,
Now, you want to know what should be the internal dia, right? What should be
right,
the
sir.
internal dia? That is D1. It should be on the basis of which stress that are actually coming on it, not the allowable.
Mm.
Did you understand?
Yes, sir.
We are not concerned, and it is already said in the problem itself, the allowable stresses. It has not said the actual stresses or the intensity of the stress. It has not said that. We need to calculate that, and we
Okay.
need to see that whether it is within the permissible limits. We need to always check whether any of the structure that you are analyzing is within the permissible limits, because that permissible limit is actually material property. Every material has different allowable permissible limits. Okay, that is
Understood,
why
sir.
we are actually calculating the actual value of stress here. Now when we have to restrict it to the actual stress, that means we want stress. Firstly, let's calculate stresses now, and we know it is simply load per unit area. Load per unit area, right? And your load is, how much is your load? Load is 6,000 kilonewton. That means 6,000 into 10 raised to the power of 3. And you have area. That is equal to stress. How much are the stresses now? Stresses are 142.87. Got it? We have not given 150. That is only allowable. So you can calculate your area here. Area will be equal to, calculate, give me value of total area that is to be needed. Give me the value of area quickly. How much is the area? इतना टाइम नहीं लगना चाहिए.
41.9 multiplied by 10 to the power 3.
Sorry, what is it?
So 41.9 multiplied by 10 to the power 3.
Okay, 41.9 into 10 raised to the power of 3 mm square. Is it correct? Has anybody else done this?
Correct.
Louder?
Yes, sir, it's correct.
Okay. So we have total area. Now among the area, what are we in need of? We are in, if we want to check what will be the internal diameter, it will be simply that area will be equal to pi by 4 capital D minus small d, and that will be equal to pi by 4 capital D. What is capital D? External diameter, that is 350, sorry, it is square, d square and d square minus internal d square, right? And that is equal to how much? 41.9 into 10 raised to the power of 3. And from there you will be able to get the internal diameter. Calculate the value of that internal diameter. Quickly give me the value of internal diameter. Is it done?
Two 262.67.
Sorry, how much is it?
262.67.
262.67. Okay. 262.67. 67 units mm. This is your internal diameter. In order to carry a load of how much? 6,000 kilonewton, which was coming on this 6,000 kilonewton. And we wanted to know how much should be the thickness. Now, if you want to calculate the thickness of this hollow cylindrical column, you can simply do that, right? Thickness can be calculated 350 minus 262.67. It is 87. You need a thickness of 87 mm in order to make this hollow circular cylinder safe enough to carry 6,000 kilonewton of load, actual load. I hope you have understood this problem. Shall we move ahead?
Yes, sir.
Okay, we'll please rejoin again, because now practice various other types of problems yourself also, in order to understand it properly, get a deep see through of how we deal with, or how we calculate the stresses and the strains of various materials, uh, irrespective of uh, or also when we have a different type of loading at different points, what are the stresses that are going to come, and how much amount of stresses are going to come, and how will the strain behave, and so on and so forth. Now we will try to analyze one more thing, which is called as Poisson's ratio. Does anybody have any idea about Poisson's ratio?
Sir, it is the ratio of lateral strain divided by axial strain.
Okay, good. So, in order to understand Poisson's ratio, what was the need of incorporating Poisson's ratio? We should be able to understand one thing, that whenever we have any body, any elastic body, let's take an example of rubber band or simple rubber. Whenever we exert some, let's say, tensile force on a rubber band, right, what happens? It will elongate longitudinally, right? It will elongate longitudinally, but it will also start contracting laterally, right? The thickness of that rubber band, while you are applying tensile forces, that means you are pulling it apart, right? What will happen? It will get elongated, there will be elongation, but at the same time the lateral dimension will also decrease, will start decreasing. The more the amount of tensile forces you are applying, the more the decrease in the lateral dimensions will happen. Now, just to incorporate this phenomena that actually happens in any elastic body, let's say about a simple steel member also. When we do tensile stresses, what we do? We put tension on both the ends of that steel rod, and we see towards the end of it, as I was discussing it last in last class also, necking happens. What is necking now? Necking is basically a decrease in the lateral dimensions before it finally collapses, before it finally fails. So incorporating these this phenomena, which is also called as Poisson's ratio. Now this Poisson's ratio is basically what? It is the ratio of lateral strain to longitudinal strain. Okay, you can also say we usually calculate, or we usually denote this Poisson's ratio by nu, which is lateral strain, that is epsilon. We have a uh, epsilon lateral and epsilon longitudinal, or simply lateral strain and we have longitudinal strain. Okay. Now, different things actually happen with different type of forces. Now, for example, if we are applied tensile forces, what will happen? The longitudinally it will elongate, and laterally it will contract, right? And similarly, likewise, if we are applying compressive forces on any elastic body, what will happen? Compressive forces on any elastic body. Longitudinally, what will happen? Longitudinally, there will be contraction, and laterally, it will be elongation, right? If we have simple any elastic member and we are applying compressional forces, what will happen? There will be decrease, it will get decreased longitudinally, it will decrease, and laterally there will be bulging, right? This is when you apply compressive forces. And when you have applied tensile forces, what will happen? While applying tensile forces, what will happen? Sorry, this is I have mentioned this as compression, and this is your This is your tensile forces. And on the same body, what will happen now? Because of this tensile forces, it will start shrinking laterally and it will start elongating. Right? This is when we have tensile forces. Therefore, in with regard to different type of forces, whether it's tensile or it's compressive forces, you can easily calculate the value of nu, which is also called as nu. That is lateral strain by longitudinal strain. And usually strain, we calculate strain by deflection, change in length by original length, right? Uh, so now here, let's say we have an example. We have this example now. We have a bar, okay. It's made up of simple steel, so we will not go much into it. It has same modulus of elasticity as 200 GPa. E is your 200 GPa for steel. And now if we apply a load on it, let's say axial load, it is simple axial load. And you can yourself judge which type of load is it. Is it compressive load or it is tensile load? 80 kilonewton. P again 80 kilonewton. Is it compressive load or tensile load? Okay. And it has a length of 1.5 meter. And its cross-sectional dimensions are, that means this is your 100. Okay. And this is your 50. These are its cross-sectional dimensions. Now, what I need from it is that I want to know the change in its length. I want to know change in length. And I want to know change in cross sectional or cross section. I want to know what are the changes in cross section after we have applied loads, and we know the material behaves elastically. And there will be some change when you are applying a tensile force. There will be change in tensile force. You already know that it will elongate actually and it will contract laterally. So in order to understand that, first of all, let's give the axis, notion axis. Let's say this is your x-axis, and then this is your y-axis, and let's say this is our z-axis. Okay, there will be change in which axis? There will be change in x-axis, and there will be change in y-axis. Right, there will be change in x-axis and y-axis. So first of all, let's see what are the stresses basically that are going to develop in z-axis, because the force is in the same axis. So we can simply calculate the stress in z-axis. So it will be simply load per unit area, and you know how much is load. It is 80 kilonewton. 80 into 10 raised to the power of 3 newton divided by area. How much is your area, cross sectional area? As you can see, we have cross sectional area of 100 mm and 50 mm. 100 mm and 50 mm. Let's we can bring that to pascals, newton per meter also. 0 point, let's say 0.1 meter. We have not kept it here in terms of mm. We'll keep it in terms of meter. uh, and we have 0.05. Okay, and that will be equal to, calculate it quickly. 16 into 10 raised to the power of 6. That is stresses in your z direction. And one more thing is also given, that is Poisson's ratio. Here is already given, that is Poisson's ratio for the material. It is again a material property, is already given as 0.32. It is absolutely a material property, and that is already given for this type of material. So firstly, we have calculated the stresses in your z direction, how much amount of stresses will be there in z direction. And then we can also check strain in our z direction, and that will be now, strain in our z direction will be simply how much? It will be stresses in z direction divided by modulus of elasticity, EST, for steel. So it will be 16 into 10 raised to the power of 6 is your stress, and modulus of elasticity is how much? 200 into, if you will calculate it in terms of, then it will be Pascal. Okay, it will be 200 into 10 raised to the power of 9. That will be equal to 80 into 10 raised to the power of minus 6. Okay, it will be again Newton per mm square, Newton per meter square. Here it will be also Newton per, if it is Newton per meter square here, so we need this to be also Newton per meter square. So for that we need to calculate 10 into 10 raised to the power of this. So we will be having strain in z direction as how much amount of strain? 80 into 10 raised to the power of minus 6. This is strain, sorry, this is strain, so it's dimensionless quantity, or we can also write it as mm per mm. There will be a strain of 80 into 10 raised to the power of 6 mm per unit meter, and that per unit meter is again mm. Okay, this is with regard to the calculation of your stress and strain in your z direction. Fine. Now we can say that the elongation of the bar, as it is already mentioned, that we have to calculate the change in its length, and we have to calculate the change in the cross-sectional dimensions. Firstly, elongation, that is delta L. Delta L can be simply calculated from the strain, that is equal to as L strain in z direction. Length in z direction, change in z direction. So that will be equal to change of length in z direction will be equal to strain, that is 80 into 10 raised to the power of minus 6 into length in z direction. How much is that? That is 1.5 meter. 1.5 meter, and you can calculate that change in length in z direction will be now how much? 120 micrometer. Okay, this is your change in length It is certainly this change in length is what? This is elongation in z direction. That means this bar has been elongated by an amount of 120 micrometer. It is usually quite less. Even from our naked eyes, we will not be able to see this, but there is a change in length. Okay, now comes this was about the change in the length. Now we want to know what actually happens in the cross sectional dimensions, right? We are concerned that what has happened in cross sectional dimension with regard to this. We want to know what has happened with cross sectional dimensions. They both will get reduced, right? If it has elongated axially or longitudinally, literally in both the directions, mind that it's not only in one direction. We have two direction, one is in x direction, and where we have a total width of cross section as 100 mm, and then we have 50 mm also on the other side. Now I want to know what is the decrease in the length on 50 mm side, and what is the decrease in the length, decrease in the width of 100 mm B, because you will be having B and D as the cross sectional dimensions. Now you know that there will be decrease, right? There will be decrease of these cross sectional dimension. They won't increase when you are applying tensile forces. But in the case of application of compressive forces, this is going to increase, right? The lateral dimensions will increase in that case, but longitudinal will decrease. Here it's vice versa. So in order to understand that again, we know that our Poisson's ratio nu, our Poisson's ratio nu is actually equal to simply strain in which direction? Strain in either of the direction. Strain in either of the direction. And how much is that? Firstly, as we have found that the Poisson's ratio is how much? 0.32. Okay. And the lateral contraction strain in both the axes now. Lateral contraction. Right? Lateral contraction. Lateral contraction strain. Lateral contraction strain in both x and y direction now. That will be simply equal to strain in x direction. That will be again equal to strain will not change. So will not change in either of the directions. Strain will remain same in y direction, and that will be equal to psi nu psi times z, nu epsilon times z. Now how much is your nu? That is 0.32, but it will be negative, right? It will be negative because it is contracting. So what is your Ez? That is epsilon z. It came out to be 80 into 10 raised to the power of minus 6. That will be equal to minus 25.6 micrometer per meter. This is your strain, right? This is what we are talking about, strain. Strain in either of the directions. Now in x and y direction, it will be actually Poisson's ratio times the strain in z direction, because we are incorporating the Poisson's ratio, that is contraction and elongation. Now thus, if when we have to calculate the change in dimension, finally we have to calculate change in dimensions of cross section. Change in dimension of cross section. There, your change in dimension of cross section, that is change in. Now, here we will be talking about change in x direction. Now, it won't be L. I'm not writing L because here it will be B and D, that is the cross sectional dimensions. I'll simply write change in x direction. What will happen? What is the change that will occur in x direction? Will be actually equal to epsilon, that is strain in x direction times length in x direction. Okay, and change in y direction will be equal to strain in y direction times length in y direction. Okay, that is equal to how much is the strain in x direction? That is equal to minus 12.6 micrometer. That means 25.6 micrometer into 10 raised to the power of minus 6 multiplied by length in x direction. Now this is your x direction. Now this is your x direction, right? And in x direction we have a total length of how much? 100 mm. Therefore you can write 0.1 meter here. And for y direction change, you will be writing minus 25.6 into 10 raised to the power of minus 6. That is what? It is actually the strain in x and y direction multiplied by the length in y direction. How much is the total in y direction? This is the total in y direction. It is 50 mm. That means into 0.05 meter. Calculate the values both, that is change in length in x direction and change in length in y direction. Give me the values quickly. Change in length in x direction and change in length in y direction. Give me the values quickly.
Delta x is minus 256 into 10 raised power minus
Delta x is how much? Minus
256
256
into 10 raised to the power of minus 6.
minus
6.
check it again. 256 into 10 raised to the power of
-8.
minus 8. Yes, that's true. 256 into 10 raised to the power of minus 8. Right? Or you can write it as 200 or 2.56 micrometer. And for your change in length in y direction, it will be minus 25.6 into 10 raised to the power of minus 6 multiplied by y direction. It is 50 mm, 0.05 meter. That comes out to be minus 1.28 micrometer. They both are contracting. In x direction, it is contracted by an amount of 2.56 micrometer. It is contracting. It's contracting. The width is getting shrinked by an amount of 2.56 micrometer. And in y direction, it is again shrinked by an amount of 1.28 micrometer. And it is getting elongated in longitudinal direction, right, by an amount of 120 micrometer, which we have already calculated. And this is how we actually incorporate the values of Poisson's ratio when we see that we need to calculate the amount of elongation and we need to calculate the amount of contraction. Therein, you can introduce the Poisson's ratio and calculate the amount of contraction and extractions. So this is enough for today. We'll be joining back on Monday.